Event-driven programming is a paradigm, so that means you can take it pretty much wherever you want in the software engineering world. Everywhere from very high-level things like websites, where a user pressing a button or clicking a checkbox might trigger a callback in your code, all the way down to very low-level things like microcontrollers, where getting a comms request on an I2C bus might trigger an interrupt for you to update some values. I'm talking anything in between, like microservice design. You can get the Linux kernel to wait on file descriptors so you can write event-based socket servers. There's so much you can do with this one architecture, and if you want to create reactive, responsive programs to real-world events that are unpredictable, this is kind of the architecture you want to go for. So we're going to go through it today, how to think in an event-driven way, how to structure your programs in an event-driven way, and we'll go through some code examples, of course. I think you guys are really going to like this. The first thing I want to talk about is how to actually structure event-driven programs, and if you understand this, you'll be able to apply this across any programming language, across any platform. It's just the way of thinking about them. So the first thing that I want to talk about over here is our event thread. Now, this event thread could actually be the main thread. It could be a delegate thread. It could be, if you're on a microcontroller, it could just be the main loop waiting for these things. If you're on an RTOS, it could be a task that is just blocking waiting for these things. The point is, you have to have an event thread that is waiting or listening for these kinds of events. So what I'm going to do is just draw the blocked state of this thread in black. So this thread coming down here is blocking. It's not doing anything. It's listening. It's waiting for events. So this might be a call if you're doing a Linux kernel thing, right? This would be a call to like epoll wait. If you're on a microcontroller, it might be if you're designing an IoT application with MQTT. Typically, if you're using something like Paho, this will be done in a separate thread, and you'll just be able to register a callback that runs when this thing happens. The point is, your program is blocked and it is waiting for an event. Now, somewhere along the line, you're going to have a trigger for this event. So I'll draw the trigger in red. The trigger can be anything. It could be if you're developing a messaging application, somebody sent you a message. It could be if you're developing an Internet of Things application, your Wi-Fi dropped out. It could be the temperature in your room dropping. It could be, the user pressed a button on the web page. It could be anything. The point is, at some point in your program's block state, you're going to have a real-world event that you're going to need to handle. Now, how do we actually handle this? The common term for something like this is, you've probably heard this before, it's a callback function. A callback function or an event handler. So those are two very common terminologies you'll see. You'll see callback function, you'll see event handler, you might also see event callback, or a combination of the two. Or if you're on a microcontroller, it would be called an interrupt handler. There are all sorts of names for these things, or you get a combination of them. It is what it is. But the point is, once you get this event, your code is going to wake from its blocked state and run this function. I do want to add a side note that the concept of the event thread blocking is not going to be applicable in all cases. So for example, if you're modeling interrupts on a microcontroller as events and you're not using an RTOS, you're just using raw hardware interrupts, your main loop of your microcontroller will be doing other things while you wait for those interrupts. It's not necessarily going to be blocking per se. And if you're using something like asynchronous programming, then you can of course run other async tasks while your other tasks block waiting for requests to come back in. Just thought I'd add that in there. So what's going to happen here, I'll draw the callback function in purple. You're going to come out here. You're going to run your callback function. It's going to perform its task. And then you're going to return to the blocked state. So that's essentially what's happening over here. Our callback function, which I'll just link like that, right? Our callback function gets called when the event trigger happens, and then we go back into the blocked state. You might have a more complex case where there are multiple events that need to be handled, in which case you'll get something like this, where, we're going to do this, then all of a sudden we return to the main thread, and immediately there's another event for us to handle over here, right? So you can have more complex situations like that. And that's one of the downsides of event-driven programming, is that because you're responding to real-world events, your state changes become quite unpredictable. So that's something you really need to consider when you're designing what counts as an event, what counts as a trigger, and how you structure your callbacks. Is because my state can jump all over the place if I'm getting these events out of nowhere. Like let's say I get rapid fire boom, 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 boom. And they all try and get my program to do different things. That might not be a great time for me, especially if I'm wanting to debug my application or I'm scouting through logs. Like, my code execution path is going to be jumping all over the place, like you can kind of see here. And if we've got another event, we're going to have an even worse time, right? And then we return to the block state once they're all handled. So this is kind of how you handle an event-driven architecture. You've got your event thread, which is going to be blocking. Then it's going to get a trigger. Then you're going to branch off from your execution of that main loop. It's still probably going to be in the same thread. You can delegate it to other threads. I've seen some libraries that do that. But then you'll return to the block state and wait for more triggers. So that's essentially how event-driven program structure works. So what you're going to need to do if you're designing an event-driven program, if of any capacity on any place in the stack, you're going to have to design. The main things are your triggers. So what counts as an event trigger? And you're going to have to assign callbacks. And the differentiation between the different triggers and the different callbacks it runs and how abstract and separate you want them to be is up to you. You might have two triggers that are actually very, very similar. Like, for example, the temperature in my room could drop, or the temperature in my room could go up. Those are two very similar events that are only changed by the direction. So I might have a single callback that is registered for both of them that just checks if the temperature went up or down and handles it appropriately in the same callback. So that when I'm debugging, I know that there's a single callback that I have to look at for the execution. But that's up to you as the application designer. And again, like I said, you can jump all over the place with your state. So you really, really have to be careful about how you structure all of this. We're going to jump into a code example because I know the theory stuff gets a little bit boring. I want to show you guys how you'd go about assigning callbacks and handling events throughout the entirety of all of the programming levels. So we're going to start on a very high level here. This is a React web app. And the theme of today, of course, is responsive reactive programs. So what better to start off with than React? Now, this was a project that was a team project that I did in university maybe 6 or 7 months ago. It was really, really dead simple. It was basically just a cryptocurrency price tracker. This thing is 200 lines of code. It's pretty chill. And you can see here, the HTML was not even in a separate file. You just return it like this. Really a simple project, but essentially, yeah, cryptocurrency price tracker. I want to demo this to you guys because it has interactions with a front end to a back end. Now, down here, you can see we have a drop-down menu where the user can select what coin they want to track the price of, right? And right here is where we assign a callback. So on select coin, right? That's the callback. So the user has pressed on a coin in the drop-down on this little widget thing here. I think the drop-down class was modified a little bit, but this was how you assign the callback for that. And so handle coin change, if we find out where that is, you can see here we've got set selected coin to the coin ID, and selected coin, of course, is on the sensitivity list for this particular function here, which would refresh the table. Basically, we're going to get all of the price data from the back end and do all that sort of stuff. So that was the callback. And then from there, it called this function here, which went and refreshed all of the data for that particular coin. I also want to turn your attention to await and async. So you'll notice here that we're using asynchronous programming, which in of itself lends to event-driven design. So essentially, the brief overview of asynchronous programming is that it's fake threading where your tasks that you're running or your functions that you're running essentially feel like threads, but they're not really threads. So essentially, it's a concurrency mechanism. What you get is an event loop that's going through. I'll just use a single threaded example. Like some async schedulers use multi-thread, but on a single async thread, what you'll have is multiple tasks that are running that are wanting to do things, but are able to block and resume. So for example, what we've got here, this refresh table thing, I am wanting to wait for the backend to give me the zone data for this coin ticker. So what's going to happen is that this refresh table function is going to block, waiting for this. It's going to suspend itself. Then the scheduler is going to start running another asynchronous task while this one waits. And once this one's ready, it's going to wake up. So if you can think about this in an event-driven way, the get zone data, so the response from the server, is essentially an event in that scenario. And so the async scheduler will wake it up and it'll start running again. So async design, if that was a bit of a shoehorned example, to be honest, like that response from the server, if you think about async design just as a general concept, you can do a lot of event-driven architecture in async design. In fact, async design, you can sort of model the whole thing, the whole paradigm of asynchronous programming as event-driven. But I just wanted to call your attention to that because async programming is very big, especially in high-level languages like C#, JavaScript. Python's got, asynchronous programming now. There's a lot of work in it. So now a little bit lower of an example. We're designing an Internet of Things microservice in Go that needs to talk to things over MQTT. If you're not familiar with MQTT, it's basically a publish-subscribe model for message delivery. Now that, if you think about it, is literally event-driven architecture in a nutshell. You've got messages that can be published and you've got subscribers that can receive them. That's events, right? Every time you publish something, that's an event. Every time the subscriber receives that, they are receiving the event. But this is going to be a little bit different because, of course, the natural example for MQTT is, oh, what's my callback for when I get a message? But I want to show you that events can happen in all sorts of different ways. So right here, this is a disconnect handler that I want to show you in Golang. So with Paho, which is the the library that you use typically for MQTT, you can set an on connection lost callback. So basically what this is going to do is that if the thing ever drops out, like if the MQTT connection ever drops out, it'll run this callback function, which essentially, as you can see here, all I do is infinitely reconnect until I get back on MQTT, which may or may not be a good thing, but it is what it is. But that's essentially what that does. You can register that callback for the disconnect event and it'll run when that event occurs. Okay, so this is where things get really cool. We've gone one more layer down, and here we're writing socket servers that use Linux kernel APIs. So right here, we're doing epoll. If you haven't learned about epoll, I've got a whole video on it. It's really, really good. Epoll is fantastic. Basically, it just lets you wait on multiple file descriptors. So for example, if you're running a socket server, you can wait on multiple clients to send you something, and you'll just be able to handle in the one thread the client that's actually sent you something, instead of having to spin up a thread for every client. Now, so right here, we've got the socket level event that comes in. So epoll wait will block this thread, waiting for an event from any of these clients that we have connected. And then later on down the line, we handle a protocol level event. So down here, we check the message, that the action we want, and we do different things depending on it. So this is sort of an abstraction that you can think about when you're doing your event-driven design, right? So up here, we have like a system level event. So that is, we are waiting for something from the system. And if you are writing something for like a microcontroller, that might be a button press. But then your system level event is going to then go to your application level event handler. So you kind of have a distinction there, right? When you get onto the lower levels, we've got application level events, which are, this is a status request, this is a watch request, this is a notify request from the partner, and you have a system level event. Like this is the Linux kernel saying you've got a packet of data that you should probably handle. It's just, you can think about it. There's no like finely defined rules. Like the things I just told you about, like what is a system level event? What's an application level event? That stuff doesn't really exist. It's not really defined. It's more about how you want to think about it as you structure the entirety of your system. So you've got a flow from these low-level events down here that trickle on down to these protocol application level events down here. So it's all about how you want to structure this thing. Let's get to the actual interesting part. We're going to be modeling a complex system using event-driven design as an example. Now, you guys know me, I'm an embedded systems guy. We're going to be modeling an embedded system, but what I want to get across is that you can take the thought process here and apply it to any layer of the stack. I want you to think about the process, not the example. I want you to see how I go about modeling these, how I separate my triggers, how I model my callbacks, everything like that. That's what I want you to focus on. Now, the system that we're going to be modeling today is a pager. Why are we doing that? Because I already had a pager project I had to do for university, and events are actually a really great way to model something like this. If you're not familiar with a pager, it's a bit of an older piece of technology. It's essentially what they used before mobile phones. It's a messaging device. So essentially, you are going to be able to send messages to people and get a response back. Now, this is a complex example because, first of all, if you think about what makes up a pager in terms of its components, you have to have a network connection. Because obviously, how are you going to send and receive messages? So you have to have a net connection. You have to have a user interface. How is the user going to send and respond to messages if there's no UI? In this case, we had a configuration interface, which was over USB. So you've got all of these sorts of things, and these trickle down. So from here, from the UI, we've got a display and buttons, right? And from the config, it's a USB connection with a protocol. So there's all of these trickle down things that we have to consider when we're modeling this as a system. So let's get into it. I want to dive into the network component first. So we're going to focus on this. Now, if you have a network connection, what do you need to do? You need to have Wi-Fi and you need to have MQTT. Now, if you think about these, immediately two events that come to mind are connect and disconnect. And these would be common between the two. So you'd have con shared between these two, and your discon, of course, I suppose, as well. Now, there are things that are unique to either. So, for example, when you are connected to Wi-Fi, you need a DHCP lease, so you actually need an IP address. Now, when your little modem or whatever gets an IP address, he's going to send you a message and say, hey, I got an IP address. So, you know, you're going to have, and I'll draw the unique one to Wi-Fi in green, right? You're going to have like got IP. And for MQTT, of course, the unique one is a message, right? Because you're not going to get a publish subscribe event. Like if you remember a couple minutes ago, I mentioned MQTT is a publish subscribe thing. You're not going to get one of those over Wi-Fi. And of course, on MQTT, you're not going to get an IP DHCP lease. Let's think about what we might want to have in our callbacks. So the connection callback. Now, if you think about this as a layer, Wi-Fi is a necessary component for you to be on MQTT. MQTT is a protocol on top of Wi-Fi, well, on top of TCP/IP, so you can't have MQTT without Wi-Fi. So maybe what happens in my Wi-Fi connection callback is I change state, which now lets me go and run my MQTT connection routine. And what happens if I get a Wi-Fi disconnect? Well, I'm going to have to change my state as well. If I get a message, if you remember before, I sort of talked about how there were like quote unquote system level versus application level events. This is one of those, right? So you might have multiple kinds of messages that your pager might release. Like, for example, in our university project, we had high, medium, low in terms of priority messages. You know, like obviously a high priority message, you want to do different things to a low priority message. So that's when you run your application level handler, which might be a completely different callback. It's up to you as the application designer to sort all of these things out. So that's the transition, right? We've got these system level events here, and then down here we've got our application level events. So you can draw the distinction like that if you think it helps. But if you have a much more simpler system, you might not even need to. Modeling the UI, we have the buttons. The buttons are the most obvious things that we can have events for. So we're using a microcontroller. So the buttons are most likely going to be on interrupts, right? Our interrupt that the microcontroller triggers is automatically a callback. That's essentially what you're doing. Your interrupt handler is basically the callback for the event. So you can get it to do things like, for example, switch the menu that you're on if you're using the display as a menuing system. You can get it to dismiss a message, you can get it to respond to a message. That's where we go from, as I was saying before, this system level event to the application. So what do I want to do with that button press? Do I want to respond to a message, dismiss it, blah, 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 blah. Now, another thing that we might want to model as part of the UI is the display. What kind of events would the display have? This is a big question mark, because the other ones are very obvious, you know, like the network connection, you have unsolicited events like connection, disconnection. You can't really help when those happen, but a display, isn't it just like you update it and that's kind of it? my question is, how do you know when to update the display? Your display has a refresh rate, right? So it might be a refresh rate of 60 Hz, 144 Hz if you've got a gaming monitor. In the embedded world on this particular one, I was able to achieve a refresh rate of 1 Hz. Really impressive, right? Actually, it was because it was an e-ink display, so don't at me. The 1 Hz refresh rate on an e-ink is actually kind of impressive. Anyway, neither here nor there. How do you know when to redraw the display? Because you need to redraw what's on the display in order to update things like the time or the current message that's being displayed. Well, you can have a display refresh task, which is waiting for a display refresh event. How do you trigger that? Well, let's say I want the 1 Hz refresh rate. So I have a timer interrupt on my microcontroller, right? That's triggering every 1 second. That's my display refresh event. Do you sort of see here? And this comes with practice, right? Like once you have to know that this is even a thing. Like what is a timer? If you hadn't used microcontrollers before, you might not even know that's a thing. It comes with experience, and that's when you can sort of immediately draw these conclusions like, oh, that's what that means. Oh, this is my timer that can be used as a display refresh event. So that's modeling the UI. Modeling the USB stuff. USB is a transport, right? So that means we're going to be sending and receiving data over the transport. So obviously our two events are RX and TX. In fact, TX we probably don't need to model as an event because our program is explicitly doing that on its own. So really we just have an RX event, right? And this is that system level event, which will then go onto our application, which is a protocol. Now, protocol events we might have could be a setting change request. We also might want to be able to put it to sleep remotely. So we might have a sleep request. Now, these things here you can model as events. Request response, you don't necessarily have to model as events, but you can sort of shoehorn them into that if you so want. It's up to you as the application designer. So as you can see, we've sort of modeled, we've got a baseline mapping of things that we might want this pager to do in an event-driven way. And of course, there are other ones. If you think about it, you know, you've got even more basic stuff like I2C and UART interrupts. You might want to model those as events. If you've got other peripheral devices that your pager needs to talk to, which it does, by the way. How do you think it talks to this display? It's probably over SPI or something like that. How do you think that it knows what orientation it's in? If you rotate it, if you rotate the screen, that can be modeled as an event, you know, if you've got an accelerometer on there. So there's all sorts of more events that you can identify as you dive in. But this is a very basic overview of like, how do you model a system from the top down like this? You want to split it off into these major components like we've done just here. And you want to go deeper. You go deeper and deeper and deeper, down to the lowest level that you can kind of go. And that's when you've sort of settled out all your events. And then you can divide those events into bigger abstractions. Like, you know, you might have a system level, or you might have a hardware level, or you might have a application level event. And then you can structure your code base around that. To wrap the video up, I'm going to show you the code that was actually used in that pager project that we just modeled, so you can sort of get an understanding of how it goes from the conceptualization phase to actual code. So right here, what we're looking at is the GPIO interrupt callback. So GPIO was used for the button handlers. Now, if you press a button, it'll trigger this callback. What happens here, we do a switch on the GPIO pin, and we choose an action that we want to do. And once we're done with that, what we actually go ahead and do is do an OS event flag set. So in this project, we were using FreeRTOS, or well, this is CMSys for setting an event flag, but essentially we were setting an event flag. Now over here, in this particular task, now we're using an RTOS, of course, so we've got tasks. We're doing an OS event flags wait. And if you remember, that was kind of similar to this whole ePOL wait thing over here we were doing at the socket server. You can see how these concepts sort of translate between the layers. But essentially what happens here, we then just go and check the bit mask. So the flags in FreeRTOS, and in fact in a lot of embedded operating systems, are done as bit masks. So you predefine all of your events and you wait on them and you check them. So over here we do MGMT button event mask. And if we scroll down here, you'll see this is where we handle it. So we don't necessarily have a callback per se. The callback is the hardware interrupt, which then sets the event flag in the task that's waiting, which then goes and checks it. Let's look at something else. Now, this was the communication task, and it was quite involved, so bear with me. I'll try and explain it as best I can. This was for communicating with the modem that we're using to connect to Wi-Fi. And the modem essentially just sent us ASCII over UART and to tell us what was happening. Now, we do the OS event flags wait, and what this was essentially we're waiting on a UART packet, right? So if we get an AT MQTT packet, then we'll handle it like this. Otherwise, we're going to do something else. Now we've got these events down here. Like, for example, here are the connection events that we were modeling before that do the state change. You know, here was the got IP, so we got the DHCP lease. As you can sort of see, here's a disconnect one, you know, and we changed the state as well. And that impacts this big state machine down here. What I want to get across is this was the conceptualization phase that we went through, and now you can see it written out in real code. And basically, if this state machine is correct, I'll show you here. We then go and start MQ init was basically like, let's start connecting to MQTT. So that was kind of the thing that we were doing there. And of course, once we get the MQTT connection one, we change the state to on MQTT. And once we're on MQTT, we are looking to extract the MQTT message data. That's sort of what I wanted to show you. You know, you go from the concept phase where you model out all these events and you can put them into real life. Anyway, so that was my video on event-driven programming and architectures. I hope you guys learned something. Let me know in the comments. Cheers.